Hey Ash, can you hear me okay? Ash, can you hear me? Check, check, check. Ash, can you hear me? Thumbs up. Ash, can you hear me? Can you hear me? Hello, hello. Hey Alec, can you hear me?
Yes, sir.
No, I cannot. Sorry, I just saw that.
Okay, I wasn't sure if you weren't paying attention to what I was sending. Y'all can hear me? You can see my screen?
I can't see your screen.
Can
Oh,
you
wait,
see
no,
the
no,
screen?
I'm sorry.
Oh,
I
she
can't.
can hear you now. Hello?
Yes,
Yes, I can hear you now.
but you cannot see my screen?
Oh, I can.
I can.
Yes. Okay. I'm running on a generator and I'm using my cell phone as a hotspot. So I do not know how this is going to go.
Yikes. How long have you been out without power?
About 10.
Oh God, it's so
Yeah.
cold. I'm sorry.
Well, I have a generator.
Oh, right.
And the generator is enough power to run the blower for the heater in the house, so I can keep the house warm. But I don't have internet. That's the big thing. So I have to use my phone.
Ooh.
Yeah. Do I seem real laggy?
No.
No,
No.
you're good.
Let me try writing on the screen. Okay. Oh, wait, what's going on here? Okay, let me try this. I haven't written on this screen in a while. That's all coming through?
Yeah, it looks good.
Okay. All right, I think we're going to go for it then. I'm going to keep my video off just to keep my bandwidth down. Okay, everyone, it's 1 o'clock. So thank you all for being here. Like I told a few students already, I'm still without power. I have a generator that I'm running to get power to my cell phone and my laptop and the screen that I can write on. So I have enough power to do this, but I'm using my cell phone as a hotspot for my internet connection. So let's just see how this goes. If it gets real laggy to the point where it's not even worth doing, just y'all let me know, okay? All right, so, all right. I'm gonna keep my video off just because of bandwidth issues. So if you don't want to have your video on, you don't have to either. It's up to you. I'm going to pick up in the notes where I left off last time. Let me open these up. And you'll have to excuse me because I'm on a completely different setup than I normally use. I'm on my laptop, so it's gonna be a little bit different for me here. So we were doing limits involving infinity, and we had been discussing the two types, and we had moved on to this idea of letting x go to infinity and negative infinity. I gave you just a few problems to try for homework, and we still have more problems to do. So the last thing that we actually did was, let's see if it looks like it's synced already, so that's good. The last problem we did was this one, where we took a limit as x went to infinity, and we basically got infinity over infinity, or infinity over negative infinity. And I told you we were going to do some algebra, and the algebra that we were going to do was to multiply by a 1 out front. And it was just kind of, we had to be clever in how we picked this 1. So I'm going to continue with this. I'm going to do a different problem. So I'm just going to make one up on the fly here. Limit x goes to infinity. By the way, we have our first exam a week from today, right? And so I'm going to try and send you all out some sort of review for that within the next 24 to 48 hours. And that way you can take the weekend to actually, start getting ready. And I already told you that next week, whatever we do on Tuesday will not be on the exam. So whatever we finish with today, that's what's on the exam. Okay, so here we go. Let's do this. X plus 2 over x cubed minus x. All right, let's do that. And so the first thing I'm going to do is I'm going to just kind of like do a direct substitution in here, but I'm plugging in infinity, which is more of an idea. So if I think about what happens in the numerator, as x becomes infinitely big and I add 2 to it, that's still some infinitely big value up there. And I'm dividing that by, now this is a little tricky, all right? Let's think about this. We have a huge number cubed, that should be infinite, minus another huge number, which is also infinite. And so the question becomes, what do we get when we take infinity and subtract infinity from it? So I think most students are okay with the idea that if we take a huge number and we add a huge number, that we'll still get a huge number. That's kind of like, okay, yeah, that makes sense. But what if we take a huge number and subtract a huge number? What do we get? Is it 0? I don't know, right? It kind of depends. It depends on how big that is, right? And how big that is. Maybe the first one is so much bigger than this one that you're going to get, a positive infinity still. Or maybe this infinity is so much bigger than that one that this one dominates this one and you get like a negative infinity. Or maybe they are exactly the same and you get 0. So the big thing I'm trying to get you to understand is when you have subtraction, excuse me, I'm like congested or something. It's a big question. We don't know, all right? We have no idea when you have infinity minus infinity. So the way that we can kind of determine what's happening here is by looking at these expressions, x cubed and x, and look at the power here, right? There's a power of 1 on the x and a power of 3 on the x on the other one. If you think about a big number being plugged in here, you have to, I guess, understand that cubing that number is going to be have much more of an impact than just raising it to the first power. So this infinity should dominate this one, right? Because dominate that infinity. And so this one over here is more significant. Does that make sense, everyone? Yeah. Okay, so here's another way to look at it if you don't like that. Just take that expression, x cubed minus x, and just factor an x out. And then think about what happens. This becomes infinitely big. And then you're multiplying it times an infinity minus 1. Well, infinity minus 1 is still infinitely big. And now you're multiplying two infinities together, and that should be infinite. So you can look at it two different ways. You can say, oh, the x cubed dominates the x, and therefore the bottom should be going to infinity. Or you can actually do some factoring and convince yourself it's going to infinity that way. Either way, you need to know that this right here is going to infinity over infinity. Questions?
Yes, I actually have a question.
Uh-huh.
So as you mentioned earlier, what if that second infinity was significantly larger than the first and it still overpowers it? How do you get past that?
So what if
Like
we
how-
had like x cubed minus x to the fourth instead? Let's just say that's what we had.
Okay.
Then the fourth power is gonna overwhelm the third power eventually.
So we're going by the exponents?
By the exponent, exactly. So this higher power means it's going to get bigger, much bigger than this one. This one's still going to get big, but not as big as this. You have to
Gotcha.
imagine these are huge numbers that we're raising to the fourth power. So now again, you could factor. Watch what happens if you factor. If I factor x cubed out, I get this. Now, if I let x go to infinity, I get infinity here times, then in here, 1 minus infinity is negative infinity. Right?
Right.
And now when I multiply these two together, I get a huge negative number, right? It's a huge number times a huge number. One of them is positive, one of them is negative, so I should get a negative answer. So I get negative infinity, which is kind of what you think here because the fourth power is going to overwhelm the third power. So this is going to be bigger than that. So you're going to have a minus infinity. Make sense?
Got it.
Ash?
Yes,
Okay.
thank you.
Uh-huh. Any other questions? Okay, so here's where we are. We know that this limit as x goes to infinity of x plus 2 over x cubed minus x. We said that that is going to infinity over infinity. And whenever we see that, what we're going to do is we're going to look in the denominator and we're going to see what it takes to kill off the highest power of x we see. So the highest power of x that I see in the denominator is x cubed. So I'm going to multiply this by 1 over x cubed over 1 over x cubed. You could put it back here in the backside if you wanted to, but I like to squeeze it there in the front. And then we will distribute those through the numerator and denominator. So we'll get limit x goes to infinity. And then when you pass this through, you're going to get an x on top of an x cubed, which gives you just 1 over x squared when you cancel the x's. And then when I distribute through here to here, I'll get a 2 on top of the x cubed. And this will all be over. Now I distribute on the bottom. This one will give me a 1 because x cubed over x cubed is 1. And then minus, I'll have x over x cubed on the next one. One of the x's cancel, I get 1 over x squared. Now at this point, I'm going to let x go to infinity. So when I let x go to infinity, I'm no longer going to write the limit, and I'm just going to remind myself that this one, and this one, all three of those are going to go to 0. Right? They all go to 0 because you have a fixed number over something getting infinitely big, and we took a lot of time last class talking about that, right? Fixed over infinity goes to 0. Fixed over infinity goes to 0. So all you're left with on top, well, you get 0 plus 0, that's 0 on top. And on the bottom, you get 1 minus 0. So this is just 0 over 1, which is just 0. See, it's okay to get 0 on top. You just don't want to get a 0 on the bottom. That's the big thing. And that is why when you're doing these, you want to look at the bottom and kill off the highest power of x down here. You don't care about the numerator. You just care about leaving some number that won't go to 0 there. That's what you're hoping for. Questions on this? Okay. All right. I'm gonna do another example. Before I do this example, though, I want to point something out. The thing about algebra. I cannot believe I'm streaming through my phone right now. That is crazy. I'm not even on 5G. It's 4G. So that's pretty impressive, don't you think? I don't know. It's crazy. Okay, so something from algebra. I think we're all comfortable with the idea that the square root of 4 is equal to 2, right? And that comes from the idea that we can rewrite this as like 2 squared, right? And you could say, oh, the roots kill each other off, and you get 2. I mean, that's one way you could look at it, right? Then if I did like square root of 8, I could do something like this. I could write this as square root of 4 times 2, and then I could say, okay, that's the square root of 2 squared times 2. And so because I have a 2 squared here, we know that basically that's this over here. That's going to turn into a 2 when I take the square root of it. So you can write this as 2 root 2. Let me try another one. If I do the square root of x cubed, I could rewrite this as square root of x squared times x. And then because I have an x squared here, I can pull this. It's almost like you're pulling this out and it becomes like an x out here. Do all 3 of these make sense to you all, just algebraically? Any questions here? We're okay? I want you to focus your attention on this one right here. One way to look at it, right, is to say, oh, I had an x squared here underneath the square root. So it's like I can pull an x out and it sits out here now, right? That's kind of one way you could look at it. I want you to think about it in the reverse direction, okay, in the opposite direction. If I gave you this right here, x square root of x, and I asked you to move this x into the root, then when you move it into the root, it has to get squared on its way in. So this could be rewritten as, well, you take this x, you move it in the root, so it becomes x squared, and then the x that was already there, and that gives you your square root of x cubed. So it's like when you're taking the x squared out, you're taking the squared off of it and putting it on the outside. But if I ask you to push that x back in, it gets squared on the way in. Let's see if you really understand that. What if I did give you this x cube root of x, and I asked you to push this x back in? What would happen to it as it gets pushed back in? Who wants to tell me?
X to the third.
X to the third, yeah. So we'll have the cube root, it gets cubed on the way in, and then you still have the x that was there. And so this becomes the cube root of x to the 4th. So normally in an algebra class, you're trying to get things out of a root, right? What I'm trying to show you is that you can actually push things into roots also. Now that's going to be useful on the next example that I give you right here. Okay, so here we go. No questions? All right, here we go. All right, so this one, limit x goes to infinity, 3x minus 1 over the square root of 9x squared plus x. All right, let's just first, again, talk about what's happening as x goes to infinity. So of course, 3x goes to infinity. We take away 1, we're still going to have infinitely big number on top. And then the bottom, everything underneath the root is basically going to be an infinity plus infinity. That's going to be infinite. And what do you think the square root of infinity is going to be? Still big, right? Like this number gets huge. It doesn't matter if you take square root. Yes, it will get smaller, but it's, you know, the x is getting bigger and bigger and bigger. So that will still take off to infinity. So this is bad, right? So we need that algebra. And the algebra we need is to kill off the highest power of x that we see in the denominator. What is the highest power of x we see in the denominator?
Square.
X squared, right? So we need to kill that off. All right. So when I kill it off, I have to multiply by a 1 out front, right? But the problem is I can't use 1 over x squared. Do you see why? What happens if I put 1 over x squared here, 1 over x squared here? What happens when I try and move this into the root? Well, we just said what happens, right? When you try and push something into a square root, it's going to get squared on the way in, isn't it? And if you took the 1 over x squared, if you squared it, you get 1 over x to the 4th. And that's not going to have the desired effect. We want to kill off the x squared and just make it cancel with an x squared. So we don't want this. Do y'all see that? We do not want this. So what should we use instead?
1 over x.
Just 1 over x. So this won't work. So I'm going to use 1 over x instead. Good. And that's because if we take a 1 over x and we push it in the root, it will become a 1 over x squared, right? If I take a 1 over x on the top and 1 over x on the bottom, right? We don't want that. Then when I push it into the root on the bottom, it will square on its way in. So let's go ahead and distribute through there. We get limit x goes to infinity. And then here. So that's just going to give you 3 minus 1 over x. And then on the bottom, I'm going to push it into the root first. So when it gets pushed in the root, it becomes 1 over x squared, but it still has to distribute through to both of those terms. So it's like I pushed it in, it got squared on its way in, and now it still needs to pass through the remaining 2 terms. So this will be limit x goes to infinity, 3 minus 1 over x over the square root of, let's see, 9 plus 1 over x. I just distributed that through. Now let x go to infinity. And we see that this will go to 0. This will go to 0. And so on the top, we get a 3. And on the bottom, we get the square root of 9, which is also 3. And so our answer is 1. That's a little weird, huh? A little weird. I like that. I like those problems. Are there any questions? Let's try a different one. How about limit x goes to infinity? This one's going to be a harder one. X squared minus x plus 1 over the cube root of x. Hold on, let me think about what I want this to do. Let's go x squared plus 9. All right, in the numerator, where are we headed? Where's the numerator headed?
Infinity.
Infinity, right? So this one was infinity. We're subtracting infinity. We're adding 1. But because this x squared dominates the x, this infinity dominates the other one. So those two together is really like infinity, positive infinity. And then plus 1 doesn't change anything. So the top goes to infinity. The bottom, well, infinity squared plus 9 is infinity. And then the cube root of infinity is still infinity. So we got something bad here. Okay. This is a tricky one. This is a really tricky one. So you need to multiply by something on the front side here that's going to kill off what? What do we need it to kill off?
The squared.
The squared, right? That's squared, but it's in the cube root, right? It's inside the cube root. So we need to kill off that squared. So we need to basically divide this by x squared. But that's what we need once we move it inside. You know what I'm saying? Like we need a 1 over x squared in here. So does anyone know what we're going to put out here? This is a little bit trickier than the last one.
Would a negative x work?
Negative?
1 over negative x?
1 over negative x. 1 over negative x.
Or
negative
sorry, x negative. I mean, sorry.
x. I'm not sure what you mean.
Like a negative exponent?
Like negative 1? Is that what you're saying?
Mm-hmm. Yes, sir.
Well, if you write that though, 1 over x to the negative 1 is the same as just x, because you could bring the x up, right?
Okay. Yes, sir.
Right. So, but let me ask you, Jose, what's going to happen when I move it inside? When I move it in here, what's going to happen to it?
It'll get multiplied by the 3.
Well, it's
Or
going to
the-
get cubed. It's going to get cubed,
gonna
right?
cube,
It's
yeah.
going to get raised to the 3rd power. And after it's done with that, Jose, I want it to be a what? What do I want in here? Right in front of that? To kill off the x squared, I'm going to I'm going to want what there?
1 over x squared.
1 over x squared, right? So after you're done cubing it, you want that inside, don't you?
Mhm.
So why don't we
Yes,
do
sir.
this? Why don't we do 1 over x squared out here, but then the cube root of it? See, because if I take the cube root of 1 over x squared, what happens when I move it inside is it gets cubed, right? And the cube root will go away and you will have just the 1 over x squared. And then whatever you do the bottom, you must also do to the top. Does everyone follow that? It's like, I want a 1 over x, I can't say that. I want a 1 over x squared right here, but I know that it's gonna need to get cubed to come in. So I just take the cube root of what I wanted and put it out here. And then when it goes in, it's gonna get cubed. Now I still have to deal with the numerator. The numerator is kind of a mess. Like this is a mess, but let's just do this. Let's do the bottom first, okay? We're gonna worry about the top in a minute. Okay, now I'm gonna have a cube root. And then this thing went inside, got cubed, became the 1 over x squared, and then I'm gonna distribute it through to both of these. Do y'all want me to write the 1 over x squared and distribute on the next step, or can I distribute now? Are y'all okay with me distributing now? All right,
Yeah.
it's not yet, yeah? Okay, so if I distribute now, I'm gonna get 1 plus 9 over x squared. So that's what happens if you take this in here, cube it, becomes 1 over x squared, and then distribute it to those two terms. On the top, I want you to agree with me on this. This right here, I want you to agree that that's the same as the cube root of 1 over the cube root of x squared. And that that's just 1 over x to the 2/3. Is that not the same thing? That's just properties of radicals. If you have a radical and a fraction inside, you can split into a fraction with the radical on top and bottom. And then when I take the cube root of 1, I get 1. And then this is just, I'm rewriting this. X squared cube root means x to the 2/3. So this is all just like algebra stuff with exponents and radicals. Now, any questions there? I'm doing that for a reason. I want to distribute it, right? Through the top. So when I distribute it, I'm going to go slow here. I'm going to get the x squared over x to the 2/3 minus, I'm going to get x over x to the 2/3. Then I'm going to get 1 over x to the 2/3. And then all of that over the cube root of 1 plus 9 over x squared. Questions? I'm not ready for a limit yet, okay? I want to look at these two and simplify these first. That one and that one can be simplified. Because both of those right now, do y'all see this is not a fixed number over something that's going to infinity like this one or this one? I have x's on top and bottom still. So I'm just going to use, what we know about exponents. This is the same as x to the 2 take away 2/3. That's how we do that, right, in algebra? So you'd have to get a common denominator here. That's like 6/3 minus 2/3 is 4/3. So x to the 4/3, right? That's what that would be. Following, yeah. This one is x to the first power over x to the 2/3. That's the same as x to the 1 minus 2/3, which is x to the 1/3. Is this okay, everyone, or no? We're almost there. Limit. The limit x goes to infinity. Okay, this first one right here turned into x to the 4/3 minus, okay, x to the 1/3 plus 1 over x to the 2/3 over the cube root of 1 plus 9 over x squared. All right, we're ready. We're ready to see what's happening here. Let's let x go to infinity. That goes to 0, fixed over infinity. That goes to 0, fixed over infinity. But wait a minute. What about this and this? Where do those go? What does that mean? Oops.
They both go to infinity.
Yeah, they both go to infinity. Let's see. This is the same as x to the 4th power cube root, right? That's what that is. And this one is cube root of just x, right? That's what those two things mean. So if x goes to infinity, this will go to infinity to the 4th power cube root. That's still an infinitely big number. And this one will be infinity cube root, which is still an infinitely big number. And we are subtracting them. Look, we are subtracting them. Y'all see that? We're going to be subtracting these. Can you tell me which of these two would dominate? Which of these two would dominate the other? Would it be the one on the left or the right?
Left.
Left, because?
It's
Fourth power, right?
yeah.
It's fourth power. They're both a cube root, right? They're both cube roots. It's the fact that this one's to the 4th power. This one dominates this one. So the answer to this problem is infinity. What do y'all think? What's your feeling here? Any thoughts? Any questions or complaints? Okay. All right, we move on. I want to go back to our formulas for a moment. Oh, no, the limits stuff that we had talked about before. And we've already established everything highlighted here. We've said we know how to deal with. And now we kind of we're seeing a way of dealing with infinity over infinity, right? We're seeing how we can do this now. And it's all about trying to figure out how to make the denominator not be a problem. And then once we figure out how the, what's going on, where we eliminate the denominator from being something weird, then we just see what happens, right? We just see what happens. And in the examples that I've given you, like this one, right? We had infinity over infinity. And when we did all the work, well, we got an answer. Oh God, that scared the shit out of me. My power just came back on. It's like everything lit up and things started making noise. Sorry. Let's see if it stays on. It came on earlier for a while and then it went out again. So, all right. Geez. All right, so on this one, we had infinity over infinity and our answer was infinity, okay? The one before that, we had infinity over infinity and we wound up getting a number, 1. The one before that, we had infinity over infinity and we wound up getting 0, right? The top went to 0, the bottom went to a fixed number. So we have a way of doing this now, at least an approach for it, right? Would you all agree? We're gonna move on now to another type of problem that we can run into, which is this, infinity minus infinity, which I actually kind of gave you a preview of this already just now when I was telling you which one dominates the other, but we're going to do it in a little more systematic approach. Okay. So let's try this. Let's do this one. We'll start real easy. Just to remind you. Okay, if you do x cubed minus x squared. Now, technically, you're supposed to have this in parentheses because you're taking the limit of this expression. So if you don't put the parentheses, technically, you're only taking the limit of the first expression. So I'm going to put it just in parentheses so we're clear. All right, so when we do this, I hope it's obvious, right? We've already said this goes to infinity minus infinity. And right now, I would not mind if you just told me the answer was infinity, because you could just say, oh, the cubed is going to dominate the squared, right? The cube's going to dominate the squared, so you're done. But in terms of like a procedure, I'm going to factor, right? So I'm going to pull the x squared out, you're left with x minus 1. And now when I take this limit, this goes to infinity times, and then this one goes to infinity also, and infinity times infinity is infinity. So my answer is infinity. Questions?
I did have one question.
Yes.
So when we're writing, let's say a problem, the exam, and we factor stuff out, do we need to put everything still in our parentheses? Well, mostly because of so that it doesn't look like you're doing the limit for just the number you factored?
Okay, I know what you're saying. With multiplication, it's okay because when you have multiplication there, it's implied that that's attached together. Okay. Now, if you put parentheses like this, it wouldn't be wrong. It's just not necessary here. Here, because we have subtraction, these are 2 different terms, and so you could be saying only do this on the first term. So with the parentheses, it says do this on both terms. Is that what you were asking? That was your question?
Yeah, that was my question.
Okay.
Thank you.
Okay, yep. Okay, so let's do another one. Limit x goes to infinity, and let's do this one. Let's do square root of x minus cube root of x. So I hope we see that that's infinity. That's infinity. So we get infinity minus infinity. Here, it's not as clear. Maybe it's, well, maybe it is, maybe it's not. It's not as clear because here the powers were 3 and 2, and we said, oh, 3 is bigger than 2, so it dominates. Here, maybe it's not as obvious. So what I'm going to do is this. I'm going to rewrite these as x to the half power minus x to the third power, 1/3 power, x to the 1/3 power. Okay. And now you could say the half dominates the 1/3, the 1/2 dominates 1/3, but I'm going to do something a little different. I'm going to factor this. See, like here I factor the x squared out, right? I'm actually going to factor this, and this is more to show you that you can factor it. Even though you may not think you can. Watch what I'm going to do. It's going to be kind of clever. I'm going to rewrite both of those fractions, both of these fractions with the same denominator. So this one has a 2, this one has a 3, so I could use a 6 in a denominator for both of these. So I could rewrite this as, let's see, 3/6. Just multiplying the top and bottom by 3. And then over here, I'm going to multiply the top and bottom by 2, and I get 2/6 like that. Now, the reason I did that is because now I can factor something out. Now watch me factor it first, and then we'll talk about it. I'm going to factor out, this one has 3/6, this one is 2/6. I'm going to pull out a 2/6. And now you need to figure out what you would put here and here to get back this. Hey, chill out, man. Sorry. So I need, can y'all tell me what I need here? Where this distributes through and gets me back this?
X minus 1.
Yeah, the whole thing. Okay, so you need an x right here. Is that what you're saying? I agree with the -1. I agree with the -1. Is this x? What would
that
happen if
be
you
1?
multiplied those? That's to the first power. You would add these, right? And you'd have to have a common denominator, wouldn't you? So you would have to do 2/6 plus, well, if you wrote 1 here, it'd be 6/6. And then that'd be 8/6. That's too much, isn't it? So what do you need?
1/6.
1/6. That's it, 1/6. And now if you change that to a 1/6 over here, if you added those together now, you would get x to the 3/6, which is what we started with here. Now I'm showing you this because now if you look at it this way, this will go to infinity times, and then this one over here will be infinity minus 1, which is infinity. So the answer is just infinity. Again, this was more to show you that when you have something like this, x to the half minus x to the third, that it is possible to factor something out. You just have to play around with the powers a little bit. You ready for another one? Here we go. Limit x goes to infinity. Square root of 4x squared plus x minus 2x. Okay, I'm going to let you think about that for a second. I'm going to turn my computer on, my other computer. While y'all are doing that. Okay, so do you all agree that we have infinity minus infinity here? Yes?
Yes.
Factoring here is a little bit troublesome because we have multiple terms underneath this root. It's not as nice as these problems. These were all just powers of x. So it's easy for us to just kind of like mess with it algebraically. Here, because of the two terms underneath this, it causes a pretty big problem. Do y'all agree with that? So watch what I'm gonna do here. It's not gonna be very natural, but I'm gonna do it. Ready? Here it comes. Anybody have a guess what I'm about to do here?
Conjugate.
Conjugate, exactly. I'm gonna do the conjugate. I'm gonna do 4x squared plus x plus 2x, and then square root of 4x squared plus x plus 2x. And now over here, just rewrite this whole thing over 1. Okay, equals limit x goes to infinity. All right, when we multiply out the top, right, when we do this here to here, the roots go away. So all I'm left with is 4x squared plus x. And then we know the middle two terms will cancel. I'll do those in red. We know that this one and this one will go away. They'll kill each other off. That's the design of conjugate. We've already talked about that. And then we have to do this one times this one. So that's going to give me minus 4x squared. Now, all of that is now on top of this new thing on the bottom. And these 4x squareds just so happen to cancel, which is nice. So now we are at limit x goes to infinity, x over square root of 4x squared plus x plus 2x. All right, let's do this. My generator's running outside and it looks like I have power back. I'm going to put you in a breakout rooms. Why don't y'all see if y'all can figure out how to do that in breakout rooms? And then I'm going to join in from my other computer and take over the control from my other computer. But let's put you in breakout rooms first, see if you can figure this one out. It's probably going to take me about, I don't know, 6 minutes or so to do this. Let's see. Yeah, there's gonna be about 3 or 4 of you in each room. There you go. I'll be back. Okay, I think everyone's back now. All right, so what did y'all think? Infinity over infinity, right? What did y'all come up with?
Well, what we did was we multiplied by 1/x, both at the top and the bottom.
Good. Okay, 1 over x. Now, did you do that to kill off the x squared?
Yes.
Okay, so one thing you could have, that's fine. Okay, that's fine that you did that. But one thing you could do also is you could look at the fact that this is two different terms, right? And that 1 over x will have to distribute to both of these, right? So you could just say, hey, if I kill off this x, then I'll be left with a 2. And that will keep the denominator from being crazy because it'll just be a 2 there. Does that make sense? So, but that would still be a 1 over x. So it turns out it doesn't matter. But that is correct. You do 1 over x and let's see what happens. So 1 over x on the top, you just get 1, right? You just get 1 on top. And then on the bottom, when you push, now you have to be careful here. When you push this in here, it becomes a 1 over x squared, which gives you the square root of 4 plus 1 over x. And then you have to do the 1 over x times this one, which will give you a plus 2 over here. Now you take your limit, this goes to 0. And then you'll have 1 over the square root of 4 plus 2. So our final answer will be 1/4. 1/4. Questions? We're good? So this is the first time we did this conjugate thing. Okay, I've got a few more to talk about. All right, how about this one? This is different. Limit x goes to infinity of sine x over x. Now, I tried to burn something into your brains a while back. This limit that was very important that you had to remember. It was this one, limit x approaches 0, sine x over x. And I said, that turns into 1. That was that sine junk over junk thing, right? The thing about that, this thing you had to remember over here is that the x here was headed to 0. When it's headed to 0, then you get 0 over 0. And then I told you the answer is 1, but don't ask me why right now. And I said, just believe it, take it on faith, and we move ahead, right? This is not the same problem because now we're letting x go to infinity. So the denominator is the easier of the two. The denominator is headed to infinity. Where's the numerator headed to? Sine of infinity. What the hell does that mean? Sine of infinity. What the heck? All that really means is what is the sine function doing as you head out to infinity, right? So, I mean, we could look at the graph of that. I mean, we know what it looks like, but I mean, may as well look at it. We're right here, sine x, right? If I ask you what's happening as we go out to infinity, what's the function doing, right? Let's see here. If we keep going out to the right, well, this function just keeps, oh, hold on, I need to open another program. Come on. There it is. Okay, so we head out to the right, our graph just keeps going up and down and up and down and up and down. Is that approaching a number? Is that headed to one specific place? No, right? It's oscillating. It's oscillating. And because it's not headed to one particular value as we go out to infinity, we would say the limit doesn't exist, right? This limit doesn't exist. So we're in a weird situation here. We've not had this. We have does not exist on top. If we have infinity over infinity, then we go do something, right? But when you have doesn't exist over infinity, that's something else, all right? That's something completely different. So to do this, what we're going to do is take advantage of the fact that we know something about sine. Sine of x must be between 1 and -1. We know that from pre-cal, right? It's bounded between -1 and 1. Now, I just said the key word. This is a bounded function. Bounded meaning it never gets bigger than 1 and it never gets less than -1, right? It's always between those two. It's bounded. There's a ceiling and a floor that this thing lives between. So we have this very new, unique situation that we need to know what happens when we run into something like this. So anytime we see, okay, so from here on out, if we ever are taking a limit, doesn't matter what's going to what, if we have a bounded, sorry, of something, right? If we take a limit and this thing is bounded on top and the bottom goes to positive or negative infinity, the answer will always be 0. And it kind of makes sense if you think about it. This number on top, right? This number on top, I guess in the case of sine, it can never be bigger than 1, right? It can never be bigger than 1. And 1 divided by infinity would head to 0. And then the other extreme is that it could be -1 over infinity. That would also head to 0, wouldn't it? Both cases would be fixed over infinity, which would head to 0. And anything in between is just some number between -1 and 1. So this should head to 0. Now I'm gonna prove it to you visually with a graph. Let's look at the graph of sine x over x. I went too far out here. Let me see. Oh, hit the home button. There we go. This is the graph of sine x over x. I'm going to kind of zoom it in like this so you can see it. That's kind of cool to look at it this way. That is the graph of sine x over x. And look what's happening as we head out to the right on the right side. Look what's happening as we head out to infinity. Do y'all see that? It looks like it's still going up and down, right? Still going up and down, but it's kind of getting like the peaks and valleys are getting lower. Like the top peak is getting smaller, the bottom peak's coming up. And the further you go out, it's like it's getting smashed in here. It's getting closer and closer to 0, even though it continues to cross through 0, doesn't it? Like it does pass through 0 a bunch of times, but it's kind of like being funneled in. I'll graph something else for you to help you see it. Come on. There we go, like this. Okay, let me graph something else for you. I'm going to graph 1 over x. And I'm going to graph -1 over x. Okay, so like I had said just a second ago, we said that sine x has to be between 1 and -1, right? That's pre-cal. So we're looking at this function, sine of x over x, and we're trying to see what happens as we let x go to infinity. Well, if I come back over here and I divide this by x and divide that by x, divide all of them by x, then what we're saying is that our graph of our function should live between this function and this function. I've graphed these two functions, the blue and the green. And do you see that our sine x over x lives between those two? And do you see that as we go down and we continue to the right, it creates like this funnel effect where our sine function is always between those two, gets funneled in. This is actually known as the squeeze theorem. I'm not going to get too deep into the squeeze theorem, all right? But be aware that that may come up in Cal 2. You may hear it again, squeeze theorem. I just think that by the time you get to Cal 2 and you talk about squeeze theorem again, I think it'll be easier for you to pick it up. There's a formal theorem. I want you to understand it visually. We had a bounded function that started between -1 and 1. We knew that, and then we just divided by x to make it look like the function we're interested in. And then we have this string of inequalities. Now this function, okay, this function here, sine x over x, is actually, it's not a famous function, but it's an important function. It's called a dampened or a damped oscillator. So think about like if you drop a ball, right? Like if you take a ball, basketball or something like that. If you drop a basketball, it's going to go up and down, right? The ball will bounce. So you can look at it, a sine function is kind of like telling you what a ball does. It bounces, comes back up, bounces, comes back up. But the thing about a ball is if you drop it and bounce it, when it comes up, it will not reach the height that you dropped it from. It will never come back up to the height you dropped it from. It's going to lose something in that transfer of energy. When it hits the ground, it's going to lose some energy. So it's not going to ever be able to come all the way back up. A regular sine function doesn't account for that. It's like it goes down, then it comes all the way back up, and then down, then all the way back up. So this is not very good for modeling things in the real world. We need something where it shows the bouncing, but it starts to get smaller and smaller and smaller. That's where the damped oscillator would come into play. That's too much stuff. Let me get all that in there. So here, it starts off and then it bounces, comes up not as high, bounces again, not as high. And then it just keeps doing that. That makes sense? And just eventually, right? Eventually, you could consider that it's just on the ground. You could make an argument that a ball sitting on the ground is vibrating. Could you not make that argument? Like it does. I mean, the atoms inside are moving. So, I mean, you can make an argument that a ball on the ground is vibrating in some sense. Right? Aren't all atoms vibrating? Isn't everything vibrating? Y'all know what temperature absolute zero is? Have y'all heard of absolute zero? Absolute zero is basically when nothing is moving. Like everything has stopped moving. All the atoms are frozen. That's absolute zero. It's pretty much impossible to get to absolute zero because everything's got to stop. Okay, we're going on. All right, we are going to move on. So bounded. So I want to take you back to this limit summary sheet. Okay. This limit summary sheet. The example I just showed you had a bounded over infinity, and I told you that that goes to zero, right? That's what I just said. Look here at this. All right, we've already talked about it. Fixed over infinity goes to zero. We've done this. But look on the bottom. You may or may not have noticed that, but I actually said in here, I defined what I mean by fixed here. When I say fixed, I mean that it's going to a non-zero number, like maybe the number 4 or 5, whatever, or it's okay if it's bounded. All right. So when I'm using this in this sheet here, when I'm saying fixed here, I mean it could be bounded. So a bounded function over infinity goes to zero. I'll give you one more example. Normally, bounded over infinity is going to have like a sine or a cosine in it, okay? Because you need something that's bounded. So limit, let's say x goes to infinity of, what do I want to do? Let's do cosine squared x over x squared plus 1. So the bottom goes to infinity. I don't think there's any trouble with that, right? Bottom heads to infinity. And the numerator is a cosine function, right? This is really just cosine of x, but then squared. That's what that means. We know the cosine function is stuck between two numbers, right? -1 and 1. And then we're going to square it, which means it can never be negative, right? Which means the top is really bounded between what two numbers? The numerator has to always be between what?
0 and 1.
0 and 1, right? We know cosine spits out stuff between -1 and 1, but then you square it, which means you can only have numbers between 0 and 1. So this is bounded. And therefore we know the answer is 0. And there's nothing else to do. On a test, I would just want you to put bounded over infinity. That way I know you know what's happening. All right. Let's just graph that one. I'm just curious. We're going to take cosine x. We're going to square it. What the heck? Whoa. We're going to divide it by x squared plus 1. We're going to get rid of all this crap. All right, there's the graph. Let me go back to home. There's the graph. This one is really kind of a good example of like a basketball or something bouncing, because it's like bouncing and then it comes up, and then it's like the x-axis is the ground. So it's kind of like it bounces, bounces, bounces. Now it probably would come up higher depending on the ball, right? What type of ball it is, that'll depend on how it bounces. But okay, those are called damped oscillators. Damped oscillators. All right, let me make sure there's nothing else here. No, I think we're good there. Okay, very good, very good. All right, I'm going to do another problem now. This will wrap up this section, I think. I want us to sketch a function such that these conditions are true. Now, we did this in the very beginning of class when we were first talking about limits. I gave you some conditions and asked you to draw me a graph that did that. And I told you everyone's graph's going to look a little different. Remember when we did that? It's been a while. It's been a while. So it's the same thing here. Okay, I'm going to give you some conditions, and I want you to draw me a picture of a function that satisfies these conditions. All right, so here are the conditions. First condition, I want f of -2 to be equal to 3. The next condition, I want the limit as x approaches -2 of this function to be equal to infinity. The next condition, I want f of 0 to be equal to 1. Next thing, the limit as x approaches 0 from the left of this function, I want that to be equal to 1 as well. And then I want the limit as x approaches 0 from the right of this function to be equal to -infinity. The next condition is that I want a vertical asymptote at x equals 3. Last two, I want the limit as x approaches infinity of this function to be equal to 5. Last condition, GH, limit as x approaches -infinity of this function to be equal to infinity. That's it. That's all I want. All right, so y'all want me to let you try it first for a few minutes? See if you can draw something that does this? I'll give you a few minutes. Yes, no, yes. No?
Yeah.
Yeah. Yeah. How about we take like, I don't know, 4 or 5 minutes, see what you can come up with. And then I'll do it and walk you through it. I just launched a poll. Let me know if you have it, if you've got something. Trying to see if anyone's done. Okay, y'all ready to talk? I only have a few students that have finished or think they've got something here. You ready to discuss this? So when I'm looking at this, the first things I'm going to do are to look at the things that are just algebra. So f of -2 equals 3, which means when I plug -2 into the function, I need a point up at 3. So I'm going to do that. I'm going to go -2 up 3. I'm going to put a solid dot there. That's part of my function. First condition met. The next condition that's algebra is f of 0 must be 1. Okay, so that means when I plug in 0 to the function, I should get 1. So I should have a point there. Not that. Nothing else here is algebra, like easy to figure out, I guess. So let's look at this next condition, part B. The limit as x approaches -2 of the function needs to be infinite. So that means that as I'm moving on the function, of getting closer and closer to -2, right? As I'm getting closer and closer to -2 from both sides, right? From both sides, I have to be headed to infinity. So -2, I'm gonna do something like this. I'm gonna go like this and like this. So it's almost like I have an asymptote here, because I just keep going up, you know, on both sides of this dotted horizontal line, vertical line, sorry. My graph goes up and up and up. Now, at -2, I have a dot, right? At -2, I have a dot, but that doesn't matter. The limit's about what's happening on the sides, left and right. Questions there? That's the second, that's part B, condition met. Part D says, as I approach 0 from the left, I need to be headed to 1. Right? So here on the x-axis, as I approach 0 from the left, my graph needs to head to 1. So it needs to actually head towards that dot from the left. Right? Like this. And then the next question says, the next part says, as I go to 0 from the right, I need to be going to -infinity. So as I move, you know, along the x-axis towards 0 from the right, my graph needs to be going down to -infinity. So I'm just going to make it do this.
So I've got D and E are met. Questions? How about part F? I need a vertical asymptote at x equals 3. Well, if you go back to last class, vertical asymptote, all you need for a vertical asymptote is for your graph to be going to infinity or negative infinity from either side. It doesn't matter. Because as long as from one side you're going to infinity or negative infinity. So what I'm gonna do is this, I'm gonna go up like this. This is just my choice. I'm gonna make it go up like this. So as I approach 3, I'm gonna go up. Now, what I do on the other side is completely up to me, all right? I could do this if I wanted to. I can make it go both up on this like that. That's one thing I could do. I could also do this. I can make it go down like this. But see, I don't even have to do that. I could make it actually come in here and like go to a point if I wanted to. As long as one side goes to infinity or negative infinity, then that qualifies as a vertical asymptote. So there's a lot of different answers you could have here. Does that make sense, everyone? You just need one side to go to infinity or negative infinity. So
Is it
why don't
okay
I
if both go? Sorry.
Yeah, could they what?
Is it okay if both sides go to, if we drew both sides to go to infinity?
Yeah, absolutely. Yep. Is that what you want to do? I'll do that too. All right, let's make both sides go to infinity. That's F. Okay, G says, as we go to infinity, my graph heads to 5. So going to infinity means going out to the right. And so as I go out to the right, I need to head to 5. Now 5 is up here. Draw a dotted line up here. So that's 5. My graph needs to head towards that. So I'm going to do it like this, like make it get closer and closer without ever getting there. That's headed to 5. That's G. H says, as I go to negative infinity, that means go out to the left. My graph needs to head to positive infinity. So that means as I draw my graph over here and I go out to the left, my graph needs to go up and continue to go up forever like that. All conditions are met, right? All conditions are met. I'm not done though. This needs to be a function. So I need to connect this all together. So you can connect it however you want. I'm going to do this, connect it like this. This is going to be a little hard for me. I'm going to go like this, and I'm going to actually change this. I'm going to make that one going like that. See, it still goes to 1. And then on this side, I'm just going to connect these two together like that. This one's going to be a little hard. I'm going to turn it back up and make it go like this. There. I've connected everything together. This drawing, pay attention, this drawing passes the vertical line test, right? If I draw a vertical line, I only hit the graph in one place. Your graph needs to pass the vertical line test because the condition in the very beginning was sketch a function, right? To be a function, you have to pass the vertical line test. So your final drawing better pass it. And that's it. So do you all see everyone could kind of have a different answer for this depending on how you draw things? Yes?
I have a question.
Yes.
Could you please explain H again? That's the one I messed up on. I don't understand how to draw it exactly.
Okay, so when we say X is going to negative infinity, we're saying what's happening to our graph as we go out this way to negative infinity, right? What is our
Yes.
graph doing? Well, it's supposed to be headed to positive infinity, right? Which means look at what's happening. If you were walking along this graph, here's you walking along the graph. If you start walking out towards negative infinity, the graph is going to take you up, right? It's going to start taking you up and up and up. And the arrow implies that this is just going to keep on happening. And you just keep on going and you're headed off to positive infinity up here. Positive infinity in terms of like a Y value. Your X values are going to negative infinity while your Y value is headed to positive infinity.
So we can graph this at any point past that -2 then, I guess, for this particular function?
Absolutely. You just have to make sure that you convince whoever's looking at this that it is doing that. So I could have done this. I could have done this, like if I wanted to. Watch, this would be a correct answer. I could have done this. That's still
Okay.
correct. Okay, because it is in fact, as I go out to negative infinity, it is heading to infinity. What it does between there, like in here, doesn't really matter. We just
Okay,
have to get the feel that as we go out to the left, we are eventually going up and up and up and up.
got it. Thank you so much.
Here's another one. That would work. You know, it's, you're kind of free to do whatever you want. Okay, questions? All right, in terms of homework for this section, so remember, we are not doing 1.5 right now, right? We are going, that's going to be next week, so don't do this. I would say go ahead and go after these problems now, all right? For 1.6. I'm just going to look here, 1, 2. So problems number 1 and 2, I have not shown you an example of those. But what they do is they give you a graph and then they ask you for limits. So that would be like, what if I gave you this graph? Okay, what if you didn't have any of this information, just the graph? And I asked you right now, what's the limit as x approaches 3 from the left of this function, right? If that was my question. Well, then you would go to 3, right? You would approach it from the left and you would say, where am I headed? And where are you headed?
Infinity.
Infinity, right? So that's what the first two problems are. They provide you a picture and they ask you for some limits off the picture. Numbers 5 and 7 are like what we just did. They give you some conditions and they ask you to draw a picture. All right. So you should be able to handle those, no problem. And then the 13 through 33, you know, I recommend this right here, that you do as many as you possibly can from there. This is not every single one of them, but you know what? It wouldn't kill you to try every single one of those. All right, 41 is a bonus, okay? 41 is a bonus. Meaning, if I ask you a question like that for on a test, it would only appear as a bonus question. And then I think 49 is doable. It's not, 49, I would not ask you that on a test, but it's something you should be able to read and do on the homework. Like, it's not like crazy. 41 is weird. 41 is a really weird problem because it requires you really understand some stuff from algebra. So it would only be a bonus. All right. Next thing I want to talk about, any questions on that homework wise? The next thing I wanted to do was see about the test itself. What I'm going to do here is I'm going to bring up last semester and see what their first test looked like. They got a little further along than we did. Let's take a look at their test. Do you want to look at it? We don't have to.
Yeah, that'd be good.
Sure.
Yeah.
I'm kidding. I know you want to look at it. Wait, what's going on here? I'm going to end this poll here. No. Okay. So this was my spring. So this was a year ago I gave this test. So let's just see how far it goes here. Y'all are all doing like screen captures and taking pictures right now, I understand. So use the graph below to determine the following limits. So I gave them some limits to figure out, and I gave them a picture. So from this picture, they had to tell me what these limits were. Okay. Okay, this one is sketch a function that satisfies these conditions. In this, it talks about right continuous and left continuous and continuous. We have not talked about continuity, so that would not be on your test. This, however, would be. But I would say this is not a good question to go off. Go off the one I just gave you. The one I just gave you is like this, okay? Draw me a picture. All right, evaluate a limit. Let's see, what is this limit doing? What is this limit doing? Let's see, what is it doing? Top's headed where?
7,
7, bottom's headed where?
21.
21. Okay, is that a problem?
No.
No, don't go factoring. Don't be doing crazy shit on this. Just that's just a number. Move on. Okay. Next one. Evaluate this limit. Limit goes to 3. Plug it in. Let's see. 9 plus 6 is 15. Take away 15. We get 0 on top. And then 3, 9, 9. Okay, 0 on the bottom. 0 of 0. Bad algebra, right? Probably factoring there. Yeah. More of the same. 0 over 0, algebra. Difference of cubes, maybe? Or you just expand out the 2 plus h cubed? I think that's a problem right out of the homework. Plug in 9. 0 over 0. What would you do?
Conjugate.
Conjugate. Oh, your favorite. Plug in 0. 0 of 0. Tangent of 0 is 0. So 0 of 0. Peel it all apart, right? Rip it apart, break it into pieces, and then start doing that weird magic where you insert things and move things around and make things work the way you need them to work. Skip it. Nope. Number 8, no. We haven't talked about continuity yet. Another limit. Approach -3 from the left. So you plug -3 in. Be careful. -3 on top does not give you 0, right? -3 on top gives you 9, take away 3. That's 6 plus 6, you get 12 on top, don't you? And on the bottom, you do get 0. Fixed over 0, right? Number line. Approach -3 from the side, see what happens, right? Fixed over 0, all you care about is what's happening with the signs, right? You're either gonna get infinity, negative infinity, or does not exist. So far, is this looking like within reason to you? Like this should not look like a surprise. Like none of this should look like crazy stuff. We've done all of this. Infinity. Infinity on top, infinity on the bottom, right? You get infinity over infinity. That's what we were doing today. So we probably want to try and kill off that x squared on the bottom. Multiply by x squared on top and bottom. 1 over x squared on top and bottom. Distribute through. You're done. I was going to say there's got to be more. Okay, this is like the one I gave today where you had a square root here. So when you're trying to kill off that 4x, that's almost the same problem that I did today. That'd be weird if that was, because I just kind of pulled that out of my head. That'd be so strange if I pulled the exact same problem out of my head. Where is it? Was it this one? Was that the one I did? Yeah, okay, maybe it's not. I don't know why that looks so familiar to me. Okay, so you know what to do with that, right? Please tell me there's more. Oh, okay. Infinity minus infinity, right? There's actually a couple of ways to do this one. You could do a conjugate. You could also do a factoring, kind of up to you. Okay, we did not get this far. We did not get that far. We did not get that far. Okay, so that was the test. So there's few topics on here that you haven't seen. So what I would expect is something like this, in the sense that, you know, it's not going to be anything crazy in terms of like, I'm going to go find some stuff I've never talked about and give it to you and expect you to like just understand it. It's going to be within the realm of your homework problems. Now, in terms of length, that's always difficult. I have to figure out what I believe you should be able to do in a certain amount of time. So my rule of thumb for Cal 1, make a test, take the test, time myself, multiply by 5, and that needs to be less than 100 minutes. So your test can be an hour and 40 minutes. It'll take us 10, 15 minutes to get started. So it's actually going to be closer to like 85 minutes that you have for the test. So I want to make sure that it doesn't take me more than like, I don't know, 15 minutes to do it. If I can do it in 15 minutes, you should be able to do it in 85. So that's usually about what I do with that. Questions?
Do we have to have any specific setup for the test?
Setup? Yes, 17 minutes. Yes, so yeah, let's take time to talk about it. We still have 4 minutes, and I'm obviously not starting anything new right now. So what you're going to do is you're going to come into class just like this, right? And the first 10, 15 minutes is just going to be getting ready for the test. So everyone will come in. I will email everybody the test. Whoever's here gets emailed. All right. If you're not here, you don't get emailed the test. And then I will also post it in the chat. Either way, I'm going to send you the test electronically. At that point, you don't even have to be on camera. I don't care. It's just, you need to handwrite the test or print it. I hope you have a printer. If you don't have a printer, you have to handwrite it, and that sucks, but that's the way I do it. So especially if you have to draw graphs, right? Like that might suck if you have to draw this graph before the test starts, to write that, copy all that, right? But you know, it's the way it is. So we'll take that time. As soon as you have printed the test or handwritten the test, once you've done that, then you will make sure your camera's on, and you must have your camera positioned in a way that I can see you and your entire workspace. So for everyone who's on camera right now, that would not be okay. What you need, and this is in our, let me go to our main page, our Canvas page. I think this is what you're asking.
So this would be all right then, or would it not be?
Oh, Kevin's asking. I was like trying to figure out who's asking.
Yeah.
Yeah, Kevin, can I spot? Why is this not loading? What the hell? Is the aces down?
I'm on it.
Yeah, I don't know why I'm not able to log in.
Actually, I
You-
think the courses, you know, first picture of the course in the home screen, I think that's the setup you said you wanted, right?
Yes, exactly. Now I actually have it somewhere else. So let me just go grab it. Just give me a minute. Okay, here we go. This will be good enough. So this is kind of what I'm looking for here. All right. So since we're here and we can talk about it, Kevin, what you have, and James, what you have, it's not exactly what I'm looking for. Only because, like, Kevin, your camera's, well, I can see what's in front of you, right? You have a monitor in front of you. That's better. The further back you can get, the better. If you can move away, because then I make sure you don't have like all of your homework problems taped up to the wall, you know? And it's not that I don't trust you, okay? It's that I don't trust you, okay? I don't trust anybody, because I have to act that way, because I want this to be fair. You know, I want everyone to have a fair opportunity to do well. And so I need to maintain the integrity of what we're doing here, right? Makes no sense. I know of Symbol Lab and shit. You can take pictures of math problems. It'll give you answers. I mean, there's so much out there now. I know that. So I'm going to try and make this even playing field. So you get your camera set up the best you can, right? You've copied or printed the test. And then at that point, you are going to make sure your desk is cleared off. And you're going to take, what you should have on your desk are your formula sheets, which you have had since day one. They're in Canvas. Those have to be printed out. You can have those, blank paper, and then the test that you just wrote down or printed. So you set up your camera, and then you say, I'm starting the test. You send me a chat in Zoom. You say, I'm starting the test. Okay. At that point, you will go and you will show the camera every page that's in front of you. Okay. That's just to make sure that you have, you know, the formula sheets, blank paper, and then the test you copied down, and nothing more. All right. Then you start the test. You just, you know, work it like you would your homework. You write everything down. When you finish the test, you send me a chat. You say, I'm done. And then at that point, the clock starts for you. All right. When you say I'm done with the test, you can leave the Zoom session. You don't have to stay in it. You can go. But you've got like 10 minutes to get me the test at that point. I'll stretch it to 15 on this first one, but within the first 10 to 15 minutes, you have to take pictures of all your work or scan it or however you want to do it. You've been doing it already with your homework and stuff. So you're going to get all those images compiled to a single PDF file, and you will send it to me. And now I'm going to send you a link. I haven't sent it yet, but I will send you a link in your email to upload the exam. And that's it. Then I will hand grade the exam, hand grade them. I'll bring them in electronically and I'll write on top of them. And then I will, when I put your grade in, I'll put an attachment in there and it will have your graded exam. So you can go and look at like where I took off points. Does that all make sense?
Yes. For the link, will it be to kind of like the first one we did? The sort
Link?
of
Link of-
no, that I meant the uploading, because you had some sort of Microsoft SharePoint Dropbox
Yeah, it was
sort of
yeah,
system.
it'll be that. It's because it's easier for me to download them and put them into my OneNote and grade them that way. Yeah, so it's different than the handwritten homework links, right? That's different. It'll be a dedicated, it's for my OneDrive. So, and you have to have your camera on, you have to have it in the right position. Like I guarantee you, no matter what happens, I'm going to be sitting here telling somebody on the day of the exam and be like, hey, your camera's not good. And they're going to like move their camera like this. They're going to just do this. All right, is that better? And I'm like, come on, you know, like, so we're going to deal with somebody in this class who can't figure out the camera thing. I'm a little more lenient on the first one in terms of being patient with you, but it's distracting to everybody to sit here and have to keep, you know, nope, that's no good. That's no good. So hopefully everyone will get it all set up and be ready for it. And then we'll see what happens, you know?
Professor,
Mm-hmm.
is all this homework due on Monday?
The only thing that I care that you do for Monday would be through 1-6, not one, sorry. Yeah, through 1-6, not 1-5. So nothing with 1-5. Yeah, we just didn't get to it. We are significantly behind. I mean, we are pretty far behind because we're just finishing the second week of school? Is this second week or third? Jesus.
It's the second.
Wait a minute, today's the third, right? So we had,
Yeah.
did we lose a day in this class?
We did.
We did?
Yeah.
Oh, they canceled class, right? Because of inclement weather. So we've only had, this is our 6th meeting on the calendar, but we've only met 5 times, right? So we're behind. We're behind. We're supposed to have 3 other sections done by right now. You know, it happens. So yeah, so any other questions? I mean, make sure you have your camera on. I always recommend just using your phone for your camera. Like get the Zoom app on your phone and then log in through your phone when you're taking the test. That way you can move it, put it in a different position. You just can't have a computer on in front of you during the test. And I need to see that. I need to see that you're not there. I've had students, you know, they've got their mouse underneath, and they're sitting there and they're looking over here, and you know, I hope I don't have to deal with that here. I hope I don't. But just as a, you know, forewarning to you, I know it's time, you can go if you need to. I mean, I don't have any tolerance for cheating, just none at all. You cheat, I drop you from the class, I report you to the college. If you want to, you know, fight me on it, then we've got video and we can have someone look at it and see if they agree with me or not. You know, but I don't tolerate it. So just, I want to see what you know. And if you don't know, then we need to work on that. We need to see how we can get you up to speed. Yeah. Okay.
Thank you. Have a good
Yeah.
week.
Yeah, I'll be in my office hours unless my power goes out again.
Thank you.
Thank
See you
you.
later.
Have a good
day.
weekend.
Yep.